I guess we'll wait until it shows that it's recording. Okay. So, all right, my cat is like trying to jump me on my keyboard. Today we'll wrap up what we covered so far on the CPU side into I guess to prepare all of you for the midterm, and now you all know how the CPU actually work, right? And one thing that I would like to point out, right, is that many of you, when you buy your CPU or when you talk about the CPU, I believe that many of you never even heard about this out of order scheduling, right? But this is one of the, and also like a complex branch prediction, and also this like instruction windows and many components we cover today, like precise exception and all those concepts, right? They are added for performance and to make sure it still run according to how you design the chip to be from the ISA perspective, right? And I sure hope that now you learn basically what you bought when you buy a computer, right? It actually not just a simple in-order processor that you might have learned from your undergraduate degree, right? Where you have a 5-stage pipeline and that's all, right? And then in the processor might be deeper pipeline stages. There's a many components like multi-scalar, which is one of the paper that I definitely recommend you to check out. It's on the reading list, right? Which is kind of like a next extension of superscalar architecture. Things like out of order, how is that done, right? There's so many engineering knowledge going into the design of the CPU that happens even nowadays, right? They still have to invent new architecture to put on top of the old architecture that they have in the previous years. And you can see the improvement from new chips that come out, right? Both on the Intel, AMD sides, as well as the Apple side and the Qualcomm side that came up with new mobile processor, server processor, CPU, typical your desktop processor, right? They all are geared toward running the desirable benchmark, the program that's supposed to be run on mobile, server, and your desktop, right? And today we'll kind of wrap up and prepare you all to transition into what happened with the main memory. But what considered so far is fetching is almost free, like one cycle. Accessing data is almost free, one cycle. But these are both not true, right? That's the key thing. Both are not true. Why is that the case? Fetch has to get your instruction from the main memory, right? These are all in the main memory. And from what I said so far, the memory is not free. Going into the memory contains some processes that has to be done, right? It takes time. After our midterm, we'll talk about what is the component of that time and how to make sure that we minimize that time. There are many techniques and research going into how to make sure the time is not too high, right? Memory take a long time to access, and they're also limited, right? If you've heard about virtual memory and what they're being there for, one of the benefits of virtual memory is basically to extend the size of your DRAM that you have on your computer so that it gets bigger. It doesn't get bigger out of like some black magic. There are certain things that are done to actually make sure you can feel that your memory is bigger. And there are certain bottlenecks that comes with that, right? So out of order with memory is basically means that when you have a load store instruction, right? The content in the memory has to be updated in the program order. Again, this is in order program processing. Basically, you want to make sure you finish things in order. Problem is when you have a load instruction, right? Sometimes you don't know there's the dependency between load and store, right? So let's say you store to address A, and then in the future, there's a load to address A. This is not done. It's still in the pipeline. This is starting. What does it mean? If I go to the memory at address A, can I guarantee that the new data is already there when my store is still in the pipeline? Can someone tell me that? Is it a yes or no? Can I guarantee that A is updated? Or can I guarantee I cannot do it? I cannot do anything with it. Right, let me open up the chat as well so that I can see your chat. Okay, so I think if you type it in, I can see it on my monitor right here. But yeah, go ahead.
I think we cannot guarantee that the data is updated or not.
Exactly, because the store is still processing, right? I'm still processing my store and I'm loading the new address. And now the address is the same. The problem is I cannot tell. So you have two sources of where you can get A. One source is from the main memory, right? If it's updated, you get it from the main memory. If it's not, you get it from the store instruction. Basically, you can go look back, hey, are you loading into A? Are you storing into A? If you are, give me your data, right? The next problem, I don't know this dependency because sometimes the load and store comes in this form. Right? Something like this. I'm going to load the address as R1 plus 20. Basically, this means that address is R1 plus 20, 0x20, basically the hexadecimal 20, right? When is that done? It's done in my execute stage, but you have no guarantee, right, that I know the address. So the dependency even, these relationship between the load and the store, you don't know the dependency until all the previous store finish. So to detect this dependency, there are multiple things you can do, right? You can wait and you can actually keep the list of pending store. We will today expand on this concept. There's also how to treat the load instruction. You can assume the load are always dependent or always independent, or figure out what to do with it, right? So the key here is we want to forward data, right? Forward data as aggressively as possible, as long as they are correct, right? So to forward a store data to a load, processor employs this load and store queue. So the obvious part is the load would go and search the store queue, right? After it knows the load address. This is obvious, right? I know my address. So if I know load to address, load from address X, right? You would go search the store queue. Are you storing to X? 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 And then if someone is storing to X, you take it. The problem is with out of order, right? In out of order processor, you can have store to address X right here, and then another store, I don't know the address. And then load to address X. Are there issues here? Are there going to be any issue here when I have one older store that I don't know the address, but then there's another store to X?
Yes, the other store can also be in the X. So
Exactly, right? That address, because I don't know, it can be address Y, it can be address X. If it's address X, you have a problem because then you basically have to forward your data from this store if the question mark is X. Otherwise, you get it from here, right? So the less obvious part is What if, right? What if this something like this happen? A store also need to look through the queue, right? When I have a store, and another thing that can happen is instructions are dispatched out of order. So it means that let's say this is your program order. This is program order, right? But in the dispatch with out of order processing, this is what happened. The load come first. And then you have store to address question mark. And then the last one was first store, you see, address X. So it means that the load might want to get the data from these two store, right? So when you have a store instruction, you also have to check the load queue. Are there loads that should come before me that are waiting for my address? Right, and then you also can combine this load and store queue into one single queue to kind of like minimize the cost. This depends on the design decision. Any questions so far? So can we do out of order, right? Doing a load and store. So when you write data to DRAM, what we call is it doesn't really block the pipeline. Why is that the case? Store, it doesn't use data. It produces the data to the address, right? So what you need to guarantee is like eventually you just need to write this back to the memory. So basically your data has to eventually being written back to the main memory. So future load just need to see this updated data. But for loads, they block the pipeline because you want to update register X, some register, right? With the content in the main memory at address, right? You want to put the content at that address to the register, which means that that's going to block the pipeline because I don't know what I'm going to write into the register. If someone else needs that register, it means that they have to wait, right? So again, repeat the same message. What if you're loading from store earlier? So here's the structure of how you can store this. You have the load address and the store address plus value, right? Plus, I guess address and value. So then you can, whenever you know the address, you can check the value, right? And then it's a queue. It has to be a queue that is sorted by instruction order. Why is that important? Because you need to tell the time, right? The order of your load and store, right? So you know, okay, this come before the load, this come before the store. Because if you assume out of order dispatch, you need some form of a queue. So the load store buffer again, right? It would have the one bit that say, is it a load or is that a store? To keep the information, is that a load or is that a store? Then you have the address and the data, right? And to allow the pipeline to run in out of order, right? The load store can be done independently for future instruction, except when there's data dependency. There is a problem here because if you have data dependency, how can we detect that? Right? How can we detect that? And future instruction that needs the data from this address would store when you have a store, you can forward the data to a load. And again, here's some example. You have, let's say in the program order, and all address known, right? Let's say you have a store to address X, store to Y, and then store again to X. And then you have a load to X, and then a load to Y. All right, so I will call this instruction 1, instruction 2, instruction 3, instruction 4, instruction 5. So this is the order, the program order. Basically, if you open the assembly code, this is where you see store to X, store to Y, store to X, load to X, load to Y. That's in the order of the program. This is your dispatch order, right? Let's say your dispatch order is your load to X, load to Y, right? Store to X, which are the instruction 3, and then you store to X, which is instruction 1. And then you have the store to Y. In this case, what you do first, so let me change the color to make it a little bit less messy. This thing will be put in the load buffer, right? And because the dispatch order is not the same as the program order, you can use the reorder buffer to tell that, hey, that's another pending store, right? That I don't know the address, because these things I don't know the address. So you're gonna wait until you issue the load, because the load is ongoing. You can proactively send to DRAM, right? That, hey, I want X. But if that's the old data, I have to throw it away and use the new data, which is this particular version of X forwarded to here. So when you have the store come in, it's like, oh, I'm gonna store to X, right? This would inform other load in the queue, basically say, hey, who need X? Who need X? I have it here. So you go and check the queue right here and say, hey, the first load need X, so I'm going to forward the data. Then the next store come in and say, hey, I'm going to update to X. Then again, you inform the load in the queue and check the order of this instruction. Say, hey, who is going to have to commit what instruction when? And it need to make sure that the first store happened after the second store, because the program orders 1 followed by 3, right? And then when store to Y happen, again, you inform the load in the queue so that you can forward Y into this Y, right? And that's it. Basically, you store either the load or store instruction, you store the address, and you store the value. There's also the ordering in the sense of time, right? And here are the issue. Here are the main issue. And this is like where the majority of the design decision can come in, right? Memory address is not known until you execute. So the first result is when you do register renaming, right? This is basically to ensure out of order that can basically properly manage, right, the instruction order. And on top of it, basically this allow the renaming of the register so to get to benefit. But the problem is difficult because you have dependency check, right? But this has to be done after the partial execution because the address is known in execute. And it also have to check other load and store address, right? And that's our issue. in out of order, this issue is called memory disambiguation problem. You need to disambiguate between many unknown address. Younger load can have an address ready before older store, right? You have store to X, store to some unknown address, and then you have a load to X. Are we getting it from here or are we getting it from here? No one knows. This is called memory disambiguation problems, and there are multiple solutions that you can deploy, right? To fix this, you can be super conservative. Assume that loads are dependent. So you're gonna wait until these store have its own address or the previous store have their own address, and then you can forward the data, right? So this is a conservative solution. You can be aggressive. Assume that anything unknown is independent. Assume that this particular store is not related to X, some other address, right? So if you want to be aggressive, and if you want to be conservative, the store will be assumed to be going to X, because you're gonna have to wait, basically wait for the question mark thing to resolve. And you can predict, right? You can predict basically the dependency of that load. To do this, basically it means you have two phases, detection and scheduling. When you detect, option one is you wait until all the store are committed. This is a flow. Option two is you ending store, things in the store buffer, right? And then check if the load address would match the store address. That's how you detect the dependency. This is dependency detection. To schedule the load and store, there are also multiple options. The conservative option, as we said, right? Conservative. Assume the load are dependent, which means that anything unknown in the store queue, those are stored to the address. You don't need to recover it because you are guaranteed that you're going to be correct, but it's going to be slow because you have to wait for the address to all previous store, right? So the second option is be super aggressive. Everything is independent. If you don't know the address, those are independent. I'm going to issue the load right away to memory, right? This is simple. But if you are wrong, you need to recover and re-execute the load. Basically, if you have this store to X and then store to question mark and then load to X, you are going to assume that the load is actually to this X and this is not to X, right? Not to X. But if that happened that the second store is actually to address X again, then it means that you have to basically figure out what do you do with that load. Option 3 is the same as option 2, but you're going to be more accurate, basically. It still requires recovery about misprediction. There are papers that I think in the reading list already that kind of like have a way to detect these dependency. So this is a design choices, right? You can pick one of these options and you can pick the different predictor because they are gonna impact performance. And before we go into what happened when you start to issue the load, which is the content after the midterm, I want to kind of wrap it up here, right? Any questions so far about the first half of the course, right? Right now, let's do any questions so far with the load stock queue. Okay, I assume there's nothing so far, right? If it's clear, Good. Then any question from the lecture 1 to 7? These are some key topics, right? Moore's law, Amdahl's law, von Neumann versus data flow, ISA, microarchitecture, single cycle and multi-cycle architecture, pipelining and data forwarding. So this is essentially your lab 1, and this is your lab 2, right? Branch prediction, which essentially would become lab 3, precise exception and out of order scheduling, and load store handling. Any question from these lecture that you want to make, basically ask me to clarify things? So the next step is like, I'm gonna open the floor for you, and you can ask whatever question you have from the previous exam that we have on the Canvas. Okay, if there's no more question, let's get it from the sample exam. Any question from the sample exam? Did you get the chance to look through this?
Yes.
So any questions that I can help?
Sir, actually, you haven't uploaded the lecture 6, and it is a request to kindly upload that.
Oh, sure. I would just like to give me 1 minute. I'll do it right now.
Yes. And the slides are also not opening. It says that it is a part of an unpublished module.
Yeah, lecture 6, right? And then let me upload lecture 7 as well before I forget. All right. Here's the course file. Okay, so the out of order execution should be uploaded and published. And now I'm doing the lecture 7, which is this lecture. I'll make sure it's up with the new slides as well for this year. And thank you for letting me know of that. In the future, if you got that problem, just ping me right away in the email. All right.
All right. And
the review, I opened up the review. I give you all 1 more week. Basically, check the deadline, because I give you extra time for the review that I forgot to open. I did set the date wrong. It was last year date. So that's what happened. That's why I didn't show up. So the assignments, if you go to assignments now, the review is open up to week 11, which is the end of the October. Check the due date carefully, because the week 5 and week 6, if you actually follow our schedule and do the review and have it on your computer already. So week 6, I extended to September 30 next week. Week 7, I'll also extend it to September 30, and then week 8 we will resume, and that's October 7. And then they're gonna be basically every week there will be another review opening up until the end of the lecture. Which I think have actually not 15, but about 18, probably 17 to 18. So you can basically collect anything after the 6th review, right? After the 6th review that you do, that goes into your extra credit. based on the same rate that we have on the first lecture. All right.
Yes.
Okay, and don't forget to do lab 2. How's lab 2 so far? How are you guys doing on lab 2?
Yes, I have formulated the basic sketch and I'm now coding the lab 2. And
Okay.
yes.
Okay, so yeah, I think coding lab 2 with 2 weeks, there should be plenty of time to finish. So I hope you both like finish lab 2 and then lab 3 would open up. I can actually, well, no, I cannot open it up now because if I open it up, you might see the solution. I can open up lab 3 whenever lab 2 is due, and that is gonna I'll give you more like 5 more weeks for lab 3 to finish. Basically, there'll be 3 labs and the project, right? And 6 review. Uh, for the exam, do you have any questions? Oh, anything else that I forgot on the canvas?
Not on the canvas, but on you haven't uploaded the lecture 6 on YouTube as well. I was checking that.
Oh, okay. I will make sure I do it. Okay, I'm downloading the slide right now. I'll upload it whenever the slide is the video is done downloading. So it probably take up one more day.
All right. And the midterm syllabus will contain up to lecture 7, right?
Yes.
All right.
So any questions from the midterm? So first of all, be prepared to get asked something similar, and also be prepared for other open-end questions as well as topics that are not on this sample exam that we covered, right? Any questions? It's been a good, like, I mean, if you went through the exam, I think you might have things you want to ask already, right?
Well, actually, I was solving the exam, and well, honestly, I just want to revise the out of order execution. I have some problems out of order execution, so I
Okay, so
kind of
what's your problem? I mean, so like maybe we can go through them.
actually there is an algorithm cost from Swallow's algorithm, and
Yes.
I just want to revise that from the slide. So
Oh,
uh, yes, honest.
so basically the Tomasello algorithm is the same as what we covered from last week, right? Whenever new instruction come in, you would first check if it's the add. Well, basically it depends on the type of instruction, right? And then you will reserve, right? You reserve an entry over here, and you check and update this valid and tag bits. If it requires source from different register, you check the table from here. It will tell you the valid and the tag bits that you need. So let's say this is source 1 and this is source 2. Right, you basically put this here, and when things are done, when multiply are done, you declare that whoever need tag. So let's say this is right to R7, right? Then you basically put in not valid, tag is X, the value I don't know. If you have anyone, let's say this is done, you update, and you will basically update every tag in here and every tag in here that requires X. Right. Let me erase everything in case you have more specific question on the steps for this question, so I can put in some example. So do you have a specific part that you're stuck with?
No, you worked on this example in the previous lecture, and yes, I will revise that, and it will be more clear then.
Okay, how about anything else that you guys want to ask? Opa, do you have anything? I mean, to be honest, Opat, you've seen this before, so so if you still want me to clarify certain things, let me know. Otherwise, I'll prioritize Muhammad to make sure that he is clear on things, at least over here.
So can you just give us some time more, because I just want to revise the lectures, and then I wanted to solve the midterm, so I kind of downloaded the slides, but it were not there, and I want to.
Well, there's no more slot for the lecture, so the answer is no. I cannot, sadly, because there's no more slot for the lecture. I already specifically tell both of you that last week that you need to go through the exam, because if you have question, we'll use this time for you. I allocate this time for you. You need to be, Mohammed, I have to be serious here, right? You need to be more respectful of other people's time. I
Yes.
don't have any free time in the world to basically to go over things with you at your convenience. I make time for this. You did not go through the exam. It's kind of clear that you did not go through the exam, right? You might be going through the out of order questions, but it's clear that you did not go through the rest to check if you have questions.